Good afternoon, everyone, and welcome to another Quanser live webinar. I'm Murtaza. I will be your host and moderator today. This is our first webinar of the webinar series with California State University, and we are honored to have our guest presenters here. Let's welcome Dr. Lin, Assistant Professor of Mechanical Engineering at San Jose State University. Her research focuses on human biomechanics and robotics, with special emphasis on medical device development and haptic feedback for surgical robots. The other presenter we have today is Dr. Roham, Assistant Professor with the Electrical and Electronic Engineering Department at California State University in Sacramento. His research interests include distributed control of multi-agent systems, cyber-physical systems, machine learning in feedback control systems, and robot decision and control.
Hello, everyone. So my name is Roham Mahadam. I go for Roham. And I hope you had a good day so far. Here in California, it's in the morning. And I know that some people is attending this session from maybe different countries with different timelines. So I hope you all had a good day so far. And thank you for attending the session. So today I'm going to talk about educational part of the applications and my experience in working with this Quanser MathWorks company and all those implementation and developments. So the teaching strategy that I have and basically we have in Sac State, and this is not the teaching. It's even in implementation or in different application. It has three main parts. So the first part is the theory part. It goes to all things that we do in the classes, like when we teach some courses in the control systems, when we teach some courses in the optimal control, different kind of the control system, or different, even it can be in different area. There are some theory behind that. That theory goes to lots of mathematical calculation. So then the next step after the theory is the simulation, because so we need to confirm that all those theoretical calculation that we have done, it has been done correctly, all right, before we apply it to the application. And that procedure is something that even for the real-time application, we have to go through that. So then we go to the simulation part and check to confirm all those actually theoretical achievements or calculation. So once the simulation part is done, then we implement that, right? So that is a way that we apply it to the practical application. We implement that to some it's like circuits or some mechanical system, everything, and observe the result. Now, here's the thing. So whenever we do some theoretical, we do the simulation, when we apply it to the application, so we are not expecting that we see the same actually results of simulation in the application as well, right? So that is what there should be some discrepancies, and this is because of many concepts that we have in the theory. I will go over that later. Now, so the theory part is from the part that we have in the in the classroom, the textbooks and everything. So simulation implementation part is what MathWorks and Quanser helped us a lot in that part. And in order to have the students have the better understanding of how these mathematical calculations, they are related to the practical applications, all right? So there have to be a certain way from theory to the implementation and application. Otherwise, there would be a disconnection between the main concepts that the students need, especially undergraduate students need to learn, right? So I'm going to talk about the control systems because this is what the main area of my research and my teaching. So for every control system, we have three main parts. So the first part, the first element in every control system is a mathematical modeling, right? Because whenever we want to do any sort of the calculation, any sort of the analysis, any sort of the mathematical actually computation in the system, we have to know some mathematical model, right? So there are multiple ways that we do it, like block diagram modeling, frequency response, state space, like in time domain modeling, in the frequency domain modeling. So, but that is the main element of a control system that we go over that and we move forward with that. So then the next step is to do the system analysis. So the system analysis is where actually whenever we find the mathematical model of the system, and that mathematical model of the system goes over like the physical representations or the differential equations that we get from the systems, and we find out some system specifications like the system speed, like the settling time, peak time, and some sort of the characteristics of the system or frequency of oscillation of the system. Now, and then we need to perform some analysis and observe what's going on in the system. So that is what we have time response analysis, or analysis in terms of the stability. And the main part of the analysis is to observe the system behavior in different circumstances. All right. So we want to make sure that if the system behavior is desired, is something that the designer you need to make some changes in the system behavior, or no, that's fine, and you don't need to make any effort in like designing a controller. So the last part is the controller design. So most of the time you check the system, you find the mathematical model, you do the analysis, and you find out that this system is too slow. The system needs a lot of effort to modify. It's too slow. We need to have a faster system, or the system has lots of oscillation, or even the stability of the system has some issues. Then we need to do the controller design. All right. So we have to define some sort of the PID controller, or it depends on how the system is complex, if we want to do the optimal control, or if we want to apply some machine learning approaches. All right. So then we need to apply it to work on some reinforcement learning or neural network based controller. Now, so in the Bay Area, the Sac State is a university that is well known more on, it's like that power area. We had lots of meetings with the advisory board from different companies. So they are looking for, so right now the companies in the utility company, mainly they are the utilities companies, they are looking for some student with PLC programming skills and also having understanding about like PID controller. So how does that work? And all these achievements, they happen when the students have the understandings about the basic components in theory. All right. So what a controller is, and how that controller, how we can do the analysis for the system, and how we can design the controller for the system, and how different kind of the controller affects the system behavior. So these are three main elements in the system analysis. So I have been working with the Quanser actually since 2017, yeah, late 2017, 2018, when I was in my PhD, and I worked with the Quanser couple tank and the cube servo. So, and the good thing about the Quanser, which I have been working with them, is that all this equipment, they are educational based, and they do have the courseware that helps a lot the instructors. Like many labs, they are already involved and like already developed, and they have the simulation. So, and then that helps the student. This is what I have been teaching the control system laboratory and even the courses. So when the students feel that there is the direct connection between the math and the application, that is what they understand the main concept. So what the controller can actually achieve, what the controller, how the controller improves the performance of the system. So that is what I have noticed that the many of the students, they don't have any idea about when they take the control system course, and it's just a lot of math involved in like going through the frequency response analysis, time analysis, linear algebra, going through the stability and lots of those concepts. And it's just simple math, all right? And even when they simulate it, it's just a simulation, all right? So we do a lot of that simulation in MATLAB. So, but when they apply it and see that, okay, when they do the mathematical modeling, they do the analysis and the design, so that is the effect on the actual system. And how does that work? How they can see the effect of that element? That is something that we actually close the loop of the learning, of the educational part, from the theory to the application. And that is what the co-answer actually helped a lot in that, in this, like in my courses, like in the control systems and robotics. So in the second state, I actually started working with the CubeServer 3, and another great feature that Quanser provided for me as the virtual CubeServer. So the virtual CubeServer actually is the environment that virtual CubeServer has the same characteristics as the actual one, but it's a virtual. So I normally, what I do in my classes, I give the students, because it's something a student can just connect it through the MATLAB and then download the packages and the software through the Quanser. And the student can do everything at home whenever they can apply all the control actually concepts that we talk about it in the class. They do the simulation, apply it in the CubeServer, and then when we go to the lab, they apply their model. So, and this gives them to do the freedom of applying anything that they want to the hardware, right? Because the actual hardware, we should not make the system unstable or something like that, because there are some limitations for the system. But I let them student, okay, go ahead and try that in the virtual part. So then you can have some understanding if you make some gain, like very high and very low. So what will happen to the system performance? And they see it in the virtual CubeServer. And then when they come to the lab, they do the modification and see that. So, and that helps them in when they go to the industry. So we have lots of like control industries in the area that helps them when they want to go to any of these industry, have the understanding about what is the modeling, what is the simulation, and what is the implementation, all right? How to get connected. And everything here using the CubeServer is real time, right? So whenever the model makes, students make any changes in the model, they see the effect of the system. And that is what happens in the real applications. So, all right, now, so these are something that I have been working with Quanser, and we are my main area of the research. That part was mainly for the undergraduate and some sort of the graduate classes. So my main area of research is the robot collaboration or robot cooperation, or sometimes human multi-robot cooperation, which I'm working on a project as like using the virtual reality. So for the multi-agent systems or robot cooperation, so one of the main application is what we have as a DARPA project, which is a target tracking, groups of the robots with different dynamics. So dynamics, like we have the multiple UAVs and we have lots of UGVs that they are cooperating together to do some mission like target tracking. It can be like some search and rescue, different kind of the applications. Now, my actual collaboration with the Quanser is to develop. The Quanser has the studio of the robot cooperation. So they have the collaboration studio of their equipment, like they have a Q car, Q bot, and then Q drones. So, and it's a part of a cyber physical system, right? So the cyber physical system, we have a system, and every agent has its own sensor and actuator, and agents are communicating through a communication network or through their like a cyber network. Now, so the advantage of developing such lab is what I do, like some sort of the cyber attack analysis, right? So the cyber attack analysis is where even when you have a multiple robot cooperation, so when the attack goes to some part of the network, right, it affects all the agents that they are getting information in everything, you know, that is in the graph for the multi-agent system. So now, one of the main actually reasons that I work with the Quanser is that all these equipments, they are open architecture. So open architecture means that they have access to the sensor, actuator, and communication network of the entire scenario. So what I can do, I can simply go ahead, I have the simulation part, go ahead to different models and apply the attack, and then observe the effect of the attack on different like nodes in the network, and then see the effect of that. So that is the part of the attack analysis. This is what we call it, the attack analysis. Then the next step is to design some resilient control. So we have a cyber physical system, we have different agents, and even the very good part about the studio is that so we can have, when in the multi-agent system, when all the agents, they have the same dynamics, like we have all the agents that they are Q car, or all they are Q bots, or all they are Q drones, right? So we call it homogeneous multi-agent systems. We can do the attack analysis and design for the homogeneous multi-agent systems. Now, when we have a collaboration of different agents with different dynamics, even Q-bot and Q-car, they have different dynamics. So then we have heterogeneous, which makes it much more harder, right? So then the attack analysis is going to be something different. And right now I know that lots of research are going on in that area. So, but the next step after the attack analysis is the attack detection, mitigation, and attack actually designing the resilient control, right? So the resilient control is where you make sure that even though you have a network is under attack, but all the robots, they will collaborate and they'll achieve the mission, and the attack will not stop the entire network. So this is actually my future plan with the Quanser, and that's something that we are working on that. So this is actually all about my presentation, which I wanted to have within like 20 minutes. So before I end my presentation, I would like to say thank you to the Quanser MathWorks actually persons, Adam Assad, Mortaza Bora, and then Michael Lewis. He helped a lot in like whenever we had any issue in the implementation or in any kind of the simulation. The support team in the Quanser, they helped us a lot. And then thank you so much for your attention, and I will wait for any question that you may have. I think I have about like 19. I have about like 30 seconds. So Mortaza, if there's anything that I need to do, or just stop sharing.
Thank you, Dr. Roham. Yep, I think you can stop sharing and we can move on to our next presenter, Dr. Lin. We'll address all the questions near the end.
Okay, thank you.
Thank you very much.
It's a great presentation, Dr. Roham. Thank you.
Thank you so much,
Uh,
Miriam.
yeah, I'm going to share my screen. Can you see my screen?
Yes, we can.
Okay. All right. So for my presentation, Dr. Rohan already talked a lot about interfacing hardware, software, and then how does that related to research and education for our students. For my presentation today, I'm going to talk about a specific topic, which is a bilateral robot teleoperation with haptic and virtual reality feedback, one of the key research areas in my lab. And I also want to kind of relate it to Industry 4.0 and what are the needs in the current industry world for the needed skills and career preparation and readiness for our students. So thank you for this opportunity. And my name is Lin Jiang. I'm assistant professor of mechanical engineering from San Jose State University. So to start with, let's first look at the background and motivation, and also talk about what are the challenges and trends in this bilateral robot teleoperation. So we're talking about Industry 4.0 and automation, and you probably heard about this term from different seminars or webinars. So the term refers to a combination of major innovations in digital technology that are posed to transform energy and manufacturing process. We know that Industry 1.0 focus more on the mechanization, Industry 2.0 focus more on the electrification, and Industry 3.0, which is currently our status, or we're going to transit to Industry 4.0 very quick, 3.0 focus more on the automation. So when we talk about Industry 4.0, it's more of considering the industry Internet of Things, combining all the current technologies, AI, machine learning, and then create a cyber physical system that will bring a sustained and a cost-effective industrial manufacturing process. So based on that terminology and based on that requirement for our future automation and manufacturing, today's workforce or our students, which will become future workforce, needs training in the latest technology to design and build the more complex product in demand. Modern robotics, as we all know, is a multidisciplinary field that is a combination of design, development, and utilization of robotic system around various industry applications. We know that there's a lot of automation in car factories, and Amazon also developed mobile robots. KUKA provide hands-on Industry 4.0 solution for collaborative robots. And also, humanoid robots can help human for some rescue, for example, rescue applications, and for some applications that required working alone with a robot for demanding tasks. In terms of these human-robot collaboration or interaction in Industry 4.0, sorry, there are different types for that human-robot collaboration, coexistence. So, for example, this is an animation from Rapid Robotics located at San Francisco. These coexistence means that we have monitor human to see how the robot's manufacturing process goes. Synchronous. Synchronous types basically the human and the robots or collaborative robots are working together independently. So the robot will work on specific jobs, for example, labeling, tooling, sanding, and the humans will focus on like quality checking, testing, other jobs. Cooperation will be another level for human robot collaboration. Cooperation means that, for example, the humans are delivering something on the conveyor belt and the robot pick it up and then operate on them. Collaboration, which we are going to talk about it in today's seminar and then also a future trend for Industry 4.0, is the robot and the human are working together with each other. And the robot are like, for example, assistant to the human. So the research trends in the human-robot collaboration and interaction are in these couple areas. For example, the safety, considering the safety working with a robot, although we have the current like technologies that we can control the robot very precisely, but we still want to consider the robot safety while we are operating with some equipment or machine. Economics, so how does human factors affect these human-robot collaboration? In assembly and welding, how we can effectively or cost effectively and sustain to control all the tasks in manufacturing line. In medical field, so medical devices or surgical robots, that how we can utilize the help for the robots. Agriculture and also education. So in our classes or in our graduate or research activities or undergraduate research or class activities, we were always talking about integration. So it's not just that I am very good at programming, I'm very good at hardware tools. For a future workforce that is ready for a career in robotics field or in the control systems field, system integration or technology integration is very crucial. We will have to have the knowledge from our education and training. We will need to know how we can utilize our tools, not only software tools, but also hardware infrastructure. And then we integrate all these together, and then we understand how we can interface the hardware with our software skills. And then this capacity will bring us to the top of the pyramid, which is a technology integration and make us ready for the future workforce. All right. Yeah, so regarding system integration that I always also request my students, because the future workforce will request us to have a technology integration, that we not only have the basic knowledge, we also need to know how to interfere with software and hardware infrastructure and then build our capacity for the workforce. So here is screenshot from an ebook, and it's a research that has done by the ASME Society of Mechanical Engineering, focus on what are the future skills focused for Industry 4.0 engineers. Currently, we already have our hard skills or interdisciplinary skills that we are familiar with. And in the future, as you can see, the hard skills request a lot in Internet of Things, AI, machine learning, design for manufacturing, robotics, collaborative robots, human-robot interaction, AR, VR. So which means that in order to satisfy as a future workforce, we are going to train our students on those hard skills as well. So next, I'm going to talk about student-led research activity in my lab at SJSU. Most of the research projects that we are working on collaborative with Quanser and MathWorks products. So I'm going to introduce specifically how we do the robot control and haptic feedback. One of the first project that we start working on is for surgical robots. And there are a lot of previous studies on surgical robots, and Da Vinci surgical robot and also Monopoly Johnson surgical robots are already on the market and has a very good feedback. Well, the thing we focus on is how can we increase the stability and how can we consider human labor safety in the surgical robots operation? How can we enable the remote treatment for limited access to robots? The current practice and professional training in terms of surgical robots, lack of tactile feedback between the tools and hands. All the haptic feedback or the tactile feedback are from the image processing. No human factors or economic consideration for the surgeons, not only for the patients, but we also want to consider surgeons. So how they feel when they are operating telesurgical minimally invasive surgery, and how does that affect their decision during the process. And there's no modular design for switching tools. So if you see a Da Vinci surgical robot, they have 4 arms, at least 4 arms. Each arm will hold one of the tools. If we can design something that has a modular tool switch, then that will largely decrease the cost for surgical robots and make it more available to, for example, third world countries in the future. And also, surgical robots largely depending on technology and practical proficiency. All the surgeons needs to be trained before they can operate on the surgical robots, which is to them, it would be additional training out of their professional training. So one of the projects that we've been working on and published on ASME IMECI 2023 is a modular tactile end effector for collaborative robot. So the idea is that most of the surgical robot arms are equipped with collaborative arms. However, we want to know whether we can design something that can easily let the surgeons or the clinicians to switch the end effector so that we can have a collaborative robot sit at the clinic as a tool. Our preliminary work actually designed low cell for end effector tactile sensing, a linear actuator that controls the surgical forceps, and endoscope that thread through the surgical forceps to be able to see how the opening of the forceps is. And then we use MATLAB to simulate the robot movement and the Jacobian matrix, joint values, and then be able to control the end effector. So here is a demonstrated video for the modular end effector when it's moving. So the MATLAB robotic toolbox give us a really good platform for us to simulate and virtually see how the collaborative move in 3D, and then help us to design our trajectory. And then based on the trajectory, we can feed into the robot control. Another research project that we are doing is consider the human-centric haptics and virtual reality feedback. So the idea is that we're not satisfied only in the image feedback that we get from the endoscope. We want to know how does the human's decision will be affected by what they virtually see. So the goal of this project is we want to track the hand motion using the haptic glove based on a master-follower architecture. So the idea is that I'm going to train myself with a trajectory. And then after a couple times of training, I will learn my learning curve through a machine learning artificial intelligence algorithm that we develop. So I know this how fast I will be in training myself to a specific trajectory. And the next time when I'm operating on site with a similar trajectory, I'm going to wear the follower glove. And if I'm off the track, the follower glove will provide me haptic cues. So the idea of developing a human-centric haptic glove integrated with virtual reality is to provide professional trainees a platform that they can train themselves at home with like a desktop and a virtual reality glass. And then this also published on proceedings of a conference paper, Human Factor and Economic Society in 2023. Another project that I've been working on and also collaborative with San Francisco State using QARM, the Quasar Robotics QARM, and also the Omni bundle from Quasar is for the robot teleoperation. So The goal is that we want to be able to remotely control multiple robots with a haptic device and a clutch system, switch gear between different robots and operate from a remote workspace. So we are demonstrating the wearable glove with sensors that we develop, exoskeleton glove that we used. And in the operator space, we're going to control the haptic device. In a remote workspace on a Q arm, we have the force sensor. We have the camera that tell us how far we go and what we are seeing on the Q arm. And then that information feed it back to the operator and tell operator what is the real perceptional information is, and the operator will make necessary decision if they want. So here is a demonstrating video, like when we're using Quark robotic license with MathWork MATLAB, and then control the remote robot at San Francisco from San Jose State University. So we are able to see how the arm works when we control the kind of the joint control bars about the width. And then when we see the robots are moving at a San Francisco State, we didn't notice latency, obviously latencies. And then we are very happy with Quanzer product and the Quank license, because that kind of solves noises and everything we were see previously in our teleoperation tasks. And the stream server actually provide us a real-time bilateral control between the remote desktop workspace and the actual workspace. So that was our experience, and with an integration of our technologies, collaboration with multiple campuses and multiple institutions. Next, I'm going to talk about how can we empower future engineers, and what are the key necessary ways that we can train our students to professional excellence. In my lab, I usually focus on hands-on learning and training for my students. And in terms of hands-on learning, I emphasize on the practical applications. For example, if we are developing teleoperation process, I will have students experience both robots separately and utilize their coding programming skills and apply on the physical hardwares, and then learn how does that program would apply on a real world scenario. And I also focus on program solving skills for my students. So my students are going to group into different projects, and I think that really helps when they try to learn something new, especially about robotics, as it's an integration of sensors, electronics, mechanical design, and machine learning, artificial intelligence control. So in terms of problem solving skills, the students needs to foster critical thinking and problem solving abilities. And that's also essential for future industrial challenges when they go to work. Again, about system integration or technology integration. So with a rapid trend or rapid growing of our Industry 4.0, Internet of Things, cyber physical systems, and learning about all the technologies behind that will equip our students to address complex integration challenges. And also, I would like my students to have lifelong learning styles. So continuously training themselves and upskilling initiatives will make them stand out in workforce and help them remain competitive in the future workforce. So preparing students for the real world applications, which is basically the same for today's seminar, is we want to learn from the theory, just like Dr. Roham said. We learn from the theory, know the mathematics, and incorporated or integrated with simulation with the help from MathWork or Quank robotic licenses, apply to the real-world applications. Combination of all these three, or the integration of theory, simulation, and practical application, will help our students grow in the current needs for Industry 4.0 workforce. And I've been talking also with our DEC members, Department Advisory Council from Industrial Engineers. So there are some typical industrial-driven skills that they want our students to get prepared. And the path to this new Industry 4.0 workforce is first, we want to know what are the needs for the skills, and which we learned from the ASME ebook. And step two is determine the technologies needed and prepare yourself, your courses that you want to learn, and what are the learning curves for you. Step three is to get on the hands-on training in system integration, interfacing hardware and software. Step four, early practice in the real-world applications. For example, in my lab, most of our students start working in the lab projects in their junior year. Some students, or one or two students, start in their freshman year, which is also very impressive. So the early, the better. Early practice in those lab activities, research activities, and interfacing hardware, software for real-world scenarios will help students learn better. And step five is like lifelong learning, continuously skill development for adaptive workforce, sustainably adaptive to the future. So with that, I'm going to conclude my presentation, and here are some reflections from this seminar. So what we are doing here is bridging the gap between engineering education and the demand for a future workforce, which request us as educators to focus on the interdisciplinary engineering, hardware, software interfacing, generative design, and system integration to provide our students sustainable and adaptive learning skills. So by aligning our educational program with the requirement from the industry, we foster hands-on learning experience and encourage lifelong learning styles. So then we can prepare a workforce that not only proficient, but also equipped to navigate dynamic and changing Industry 4.0 future workforce. With that, I would like to thank Quanzer and MathWork for continued support, and my collaborators in along with my research path. And I also want to thank my students, graduate and undergraduate students. Some are high school students as well. And I appreciate all the time I've been working with my students in the lab, and I'm very happy to see them grow. Thank you so much, and I'm happy to answer any questions you may have.
Thank you very much, Dr. Lin and Dr. Roham, for that amazing presentation. I think we'll move on to the question and answer section of our presentation and answer any questions that have come in from the audience. Let's see. The first one is for Dr. Roham. What type of controller scenario is the Quanser Cooperative Studio?
So this is a really good question. Actually, the current architecture of the Quanser, because you know that for the collaborative robotics, the localization is the most important part. So right now it's a centralized like control, which the studio has some camera installed that takes the localization of the agents and then send it to some centralized controller. But I know that I've been working with the Quanser, and they are working hard in developing the decentralized like distributed control, and have like some you know distributed actual localization SLAM on each robot, right? So this is something that we will have it for the concert. And thanks for the question.
Thank you very much. Our next question is for Dr. Lin. What are the key challenges that educators and students might face in the process of implementing bilateral teleoperation and virtual reality in the context of robotics education?
Yeah, that's a good question. So, a lot of the challenges that we already meet in our lab, and this is really complex technology and a blend of a lot of key knowledges from different areas. So, I would just think the main challenges in the bilateral robot teleoperation and control will be the technology complexity, like how you deal with uncertainty, how you deal with the noise signal, and how you deal with communication between hardwares, interfacing with the hardware using the software. So industrial wise, I always hear a story from the industrial council that when they have new grads that working in their company, they want the new grads to start from scratch. What does that mean is they want that new grads to go and then break it down a robot and then measure every encoder values from the joints and then tell us or tell the manager how you want to control it after you know all these individual information. So that brings an question that how does is the student ready for the system integration? If not, what can we do from an educator point of view? So that's why we started to asking ourselves about that question as well. And then I think the challenges here is that we're not just mechanical engineering or we're not just electrical engineering. We are interdisciplinary, working together, and then we want to build a better environment for our students so that they can grow and then they have prepare their self for their career.
That's very insightful. Thank you very much.
Thank you.
We have another question for you, Dr. Lin. Um, this is regarding the integration of Quanza robots with other robots that operate on the ROS operating system. Is it possible to integrate Quanza robots with other systems using ROS?
Yes. So it is possible if the robot itself also support ROS in control. And one of the challenges is that the Quasar provide real-time control, and the the Quank robotic license already denoise the signals coming in to your desktop, to your server. So when you output basically a trajectory data point through the ROS channel to an external robot that you want to control. It is possible, but very challenging and very difficult because we have no idea of what the hardware is. When we receive the hardware, it may not have the open architecture. We may not have the necessary information we need in terms of control. So that is a lot of like exploration when we receive a robot arm or when we receive an external arm. So that's why when we choose to do the teleoperation between two different universities, we still choose Q-arm because Quasar built the Q-arm from scratch. So everything and every information that we request will be embedded into a Quank robotic license, which help us to utilize whatever control method that student develop only with the help of the Quark robotic license. So we don't spend much time on figuring out what our manufacturer did to their robots and then how we read all the data from the robots. Does that answer your
Perfect.
question?
I think it does. I'll add some context to that. At Quanzer, for a lot of our core solutions, including our manipulator, our unmanned ground robot, etc., we do provide ROS nodes, so you can integrate them into any simulation code that you may already have developed with ROS. I'll give Dr. Lin a break on the next question. We'll switch over to Dr. Roham. How many hours of lab time is provided for students in a typical semester at the undergraduate level?
So there's another good question. We do have I do have the controls laboratory for students. So every week we have 2 hours and 40 minutes of the lab time. But what, and this is what all the lab manuals and everything they are provided to students. So, but that is not the exact time that the students actually work on that. The students have access to the virtual lab and they try a lot. I asked them to work a lot on the lab manual, develop on the different scenarios of the lab. But the lab time, which we have every week, 2 hours and 40 minutes, they apply what they have done. So they work during a week on the lab manuals, work on that, and then during lifetime they apply it to the actual hardware, and then we go over all those mathematical calculation and everything to make sure that everything is clear for the students. But that was a really great question.
Thank you. That makes sense. Another question for you, Dr. Lin. How does the integration of hardware and software in educational settings contribute to a more comprehensive understanding of robotics and automation for students?
Yeah, that's a kind of big question, and I'm going to break it down and then discuss it. Very good question. So in at San Jose State, the integration of hardware software is starting at an early phase. So we have a mechatronic class in the junior year before the students go to capstone or senior design projects. And then the class is a combination of like all the information for electronics, mechanical design, mathematics, control systems for lectures, and then also include a lab. And then that integration actually happens when the student is doing a lab or a project. Just like Dr. Roham also mentioned about digital twin, we also would highly recommend our student do a MATLAB simulation before they run on a motor, for example. Before they want to do an inverted pendulum, before they want to control a stepper motor, we want them to know what the expected feedback will be and what the expected control they want to apply. For example, the student learned the PID, and then the student will ask, why why my I values are so small, and why my P and then P values are so large. If they do the simulation, if they figure out the root Lucas plot, and if they see all the zeros and poles, they will know that this is because of we want to drag the root Lucas to your left-hand side so that make it more stable, make the system stable. That's a key in terms of motor control. You don't want it to expand it to anywhere like you're not controllable. So simulation is one of the bridge connecting with the hardware and the software integration. Another skills that we also kind of practice our students on is debugging. So there are a lot of challenges when um, they have done the simulation and they want to apply the exact same coding on their control systems for for their whatever project they're working on. For example, a student used to design a tiny HVAC system with a heater and a cooler, um, and then build a infrastructure for that. So the control for a heater and a cooler is different, and the loop, like the feedback loop or the sensors that we used, is also depending on like what our the physical system is, what is the size of your cubic, and what is kind of conduction level for the windows and stuff. So all these factors affect the hardware software interface, and then the student need to debug themselves in the lab during the project. So that's how we train our students in the system integration. I hope that answered your question.
Yep, I think that answers it. I would like to thank the audience for the questions. They've been very helpful. And thank you again, Dr. Roham and Dr. Lin, for answering them. If you have any questions after the webinar, please visit quanzer.com or email info@quanzer.com, and we'll be happy to chat with you. Last but not the least, thank you again for joining us today. Have a great day or night ahead of you.
Thank you, Borja. Thank you for organizing and monitoring the seminar. I appreciate this opportunity, and thank you for all the audience. And thank you, Dr. Roham. I learned a lot from you, and we will talk offline.
Sure, of course. Thank you all attending. Thank you, Dr. Lane. It was great to like have your presentation. Thank you so much.
Thank you,
Thank you.
everyone.
Yep.
Yeah.
Bye, everyone.
Bye.